Welcome to a new problem solving session. And this is an old problem, I guess. I have already given it in a post. And the problem is, a long dielectric thin wall cylinder of radius r, a length L much greater than r. That makes it a long solenoid. And having a mass m carries an electric charge of uniform surface charge density sigma. The cylinder can rotate without friction around its axis under a force exerted by a weight of mass m, suspended by a light thread wound around the cylinder. Determine the acceleration of the mass m, and the magnetic constant mu naught is given, known. So I can guess that the cylinder rotation is equivalent to a circular current which generates magnetic field inside the cylinder. And to find this magnetic field, we need to find the total current flowing on the cylinder surface. And to find it, we have a formula that I is equal to q omega upon 2 pi. Obviously, q is not given, but omega is given, and omega can be written as q by the total surface area of the cylinder, that is 2 pi rl, and omega can also be written in terms of linear velocity of this mass here, and this will be v by r. V is linear velocity of the mass. And now if we write the value of q and omega in the formula for I, we will get q equals sigma 2 pi rl q by 2 pi and omega as v by r. Then we are going to get, after cancelling terms, the result, the current comes out to be sigma lb, and that is the total current flowing on the surface of the cylinder, and it is going to produce a magnetic field. And this magnetic field, I guess, inside the cylinder is that one of a long solenoid. And we know the inside the long solenoid, the magnetic field is given by mu naught Ni. Ni is total current per unit length of the cylinder. And so Ni here can be written as I upon L. L is the length of the cylinder. And putting the value of I from here, you can get B is equal to mu naught sigma B. I gets cancelled out. And this magnetic field produces some kind of magnetic energy inside the cylinder, and this magnetic energy can be written as EB, and that will be equal to magnetic energy density, that is B square by 2 mu naught multiplied by the total volume of the cylinder. So total volume of the cylinder is going to be pi r square L, and so B square by 2 mu naught can be written as mu naught square sigma square V square by 2 mu naught. And if we multiply it by the later terms pi r square L, we are going to get many things. And I would like to write this magnetic energy inside the cylinder in terms of half kV square, where k is a constant sort of thing, and its value will become pi mu naught. You can see here rho square sigma square r square L. So this is. Now we can also find that the kinetic energy of the cylinder is cylinder itself. It's a hollow cylinder, so its kinetic energy of the cylinder, we can write half its moment of inertia will be simply mr square multiplied by omega square, and omega is v upon r, so we can write it like this, so that we can get the kinetic energy of the cylinder equal to half mr square, and kinetic energy of the block, that will be simply half mv square, where at the moment when its velocity is v, and now we think we are ready to apply the conservation of energy. That is a universal principle. We don't need to justify it. And to write this expression for total energy remains constant, we can simply write the kinetic energy of the cylinder, that is half mv square, this is not mr square, half mv square, half mv square plus kinetic energy of the block, that is half mv square, plus gravitational potential energy of the block. I suppose the block has come to a distance in vertically downward direction. Suppose the distance is x at the moment when its velocity is v, it has shifted a distance x in vertically downward direction, then its gravitational potential energy will be simply minus mgx. And the magnetic energy of the magnetic field inside the cylinder, that is half k v square, and it's a constant. Now we need to do one thing, just one thing. The relation is very good. I can write it in one more step because it looks beautiful. If we simply take half b square as constant, then it's going to be a small m plus capital M plus k minus mgx, and this is a constant. And now we can do one thing. We can use the fact that velocity of the block v is simply dx by dt, and the south acceleration of the block as dv by dt. So we need to differentiate this thing, and we can do this easily. We can differentiate this thing with respect to time, and we can write half v half 2v dv by dt. b square by 2 is half 2v dv by dt, and this thing is going to remain constant, minus mg, x is dx by dt, and constant is differentiated to 0. Half gets cancelled out, and this v also gets cancelled out because v is equal to dx by dt, and we have the result, dv by dt equals mg divided by m plus k. Just write down the value of k and you will get the result as dv by dt. The south acceleration is mg divided by m plus what was the value of k? K was pi mu naught sigma square r square l. Okay, so I'm going to write it, pi mu naught sigma square r square l, and this is the result. Thank you very much for watching.